We now have third form of pigeonhole principles. In the previous lecture, we talked about two forms, first and second forms of pigeonhole principle. In the first form, we said we just need to find that at least one of the pigeonholes contains at least two pigeons. That's for first form. In the second form, we said if you have a function from x to y, let's say this x, if you have a function from x to y, we say if the cardinality of x is greater than cardinality of y, then there exists x1, x2 in x, such that f of x1 equals f of x2. This is for the second form. Now we have third form. For the third form of pigeonhole principle, we say it's actually the generalized pigeonhole principle. We say for any function f from a finite set x with n elements, if we have a set x with n elements, if we have n elements in x, to a finite set y with k elements, if in set y we have k elements, and for any positive integer s is any positive integer. We say if s is less than n over k, that means if we divide n over k and n is less than n over k, then there exists an element y in y such that y is the image of at least s plus one distinct elements of x. That means here there exists an element here. Let's say this an element such that we have s plus one elements here which have the same image, which is y, which is that point. Okay. Now we have an example. It says a box that contains 8 green balls. You have 8 green balls and 6 red balls. It's kept in a completely dark room. That means our domain, that means x contains 14 balls. We don't care about the colors. Here, B1, it's written down here. We have 14 balls in x. Okay. And the balls are only 2 colors, which are green and red. That means our range is only green and red. We have only 2 colors, green and red. What's the least number of balls? One must take out from the box so that at least 2 balls will the same color. That means if we select, how many balls should we select such that at least 2 balls are the same color? That means how many balls should we take here such that 2 of them have the same color? Look, our range is either green or red. That means the ball that we are going to take is either green or red. That means if we take one ball, it's either green or red. Okay. If we take the second one, it's also either green or red. Let's say if we take the first ball to be green, and if we take the second ball to be red. How about the third ball? The third ball is either green or red. Let's say if it's green, B3. That means here we could get 2 balls would have the same color. That means we must have at least 3 balls. We must have at least 3 balls such that 2 of them have the same color. So that's the number which is required to find. So we must take 3 balls. Okay. I'm just explaining like that. Now we solve it. Okay. We say for the solution, we set x to be the set of all balls. Here we have 8 green and 6 red. That means we have 14 balls. And y to pick the colors. We have two colors, two different colors, which are green and red. We define a function f from x to y by f of b, that means the image of each ball is either green or red. F of b is green if the color is green, and f of b is red if the color is red. Now, this is the function that we found, or that we defined. As you see here, these are pigeons and these are pigeons. Pigeons are the images. We say, if we take A to be a subset of X, A we take to be a subset of X. That means in A we have balls. How many balls should we have in A? We say we have 3 balls. If we take a subset A of 3 balls of X, that means we take 3 balls randomly. Then the cardinality of A is greater than cardinality of Y. That means the number of elements in A, we have 3 because we said there are 3 elements in it, 3 balls in it. How about the cardinality of Y? Since we have only green and red, that means it's 2. That means the cardinality of A, which is the number of balls in A, is greater than the number of colors in Y. By the pigeonhole principle, we have at least 2 elements of A must be assigned to the same value in Y. That means here we apply the second form of the pigeonhole principle. We said if the cardinality of X is greater than cardinality of Y, that means there are at least 2 elements in X which have the same image, and here we have A. The cardinality of A is greater than cardinality of Y. That means there are at least 2 elements in A which have the same image. So it means there are at least 2 balls in A such that they have the same image. Okay, they have the same image in Y. So therefore, at least 2 elements of set A must have the same color. So for this one, for this part, we can use this way. We say let A be a subset of X, A be any subset of X, and Y is the set of colors which are green and red. We say the cardinality of A to be X. We don't know how many elements do we take from X. We just say A be any subset of X. The cardinality of A, we don't know it. We just give a variable to it. We say it's X. And the cardinality of Y, since you have only 2 elements in Y, so the cardinality is 2. So S plus 1 equals 2. So from this, we say S equals 1. S equals 1. Now, by pigeonhole principle, we say S is less than the cardinality of A dividing by cardinality of Y. We don't know cardinality of A. We put X for that. Cardinality of Y is 2 and S is 1. And from this, X must be greater than 1, greater than 2. If we multiply both sides by 2, we get X is greater than 2. So what's the integer number which is greater than 2? X must be greater than 2. That means X could be 3, 4, 5, or any other number. So the least number here is 3. That means X must be 3. Okay. Here we say, let F be a function from a finite set X to a finite set Y. And we suppose that the cardinality of X is N and the cardinality of Y is K. That means we have N elements in X and K elements in Y. We let M to be the least integer function of N over K. Have you ever seen this? Have you ever heard cell and flow? Cell and flow in computer programming? Okay, I'm going to tell you that. We say the least integer, this is the least integer function. We have these 2 functions. So if you have 0.1, So the least integer function for this number is equal to 1. That means we always take the least integer which is greater than the number which is here. همیشه على أكاد الجمالي تواوي دواي خوي. What's the integer number which is greater than 1? 0.1. It's 1. Okay. Look, here we have 0, 1, 2, 3, and so on. -1, -2. So if we take a point here between 0 and 1, what's the next integer number? It's 1. That means if we take 0.1, so its least integer function is 1. The least integer function is 1. So how about, let's say, 2.4? How about this one? 2.4 is between 1 and 3. It's somewhere here. So the next integer number is 3. That means it equals 3. How about 1.9? 1.9 is, it's 2. Yeah. How about the least integer function for the integer numbers? For integer numbers, let's say 2. It's still 2. For the integer numbers, it's their cells. But for the fractions, we take the next integer number. Okay. How about, let's say, minus 0.2. Minus 0.2 is here. So what's that? It is 0. Okay. It's between -1 and 0. We take the next one, the greater one, which is 0. Okay. So this is 0. How about 0.999? It's 1. Okay. How about 0.1? How about this one? It's still 1. We always take the next one, the greater one. It's between 0 and 1. Which one is greater than 0.01? 1, not 0. Okay. It's about the least integer function. And we also have greatest integer function. I'm going to clean this. For the greatest integer function, we say if you have this one, we take the smaller one in this case. We say 0.1. What's this one? It's 0. That's a 0. Yeah. How about 0.99? It's still 0. Is it? It's still 0. And this one, let's say 3.5. It's 3. Okay. We just remove the fractional parts for this function. So this is greatest integer function. How about this one? Let's say 2. It's still 2. Yeah. For the integer numbers, is their cells. And how about, let's say, -5? It's still -5. It's the same. For the integer numbers, is their cells. But for the fractions, for this one, we take the next number, the next, yeah, the bigger one. But for this one, we take the smaller one. Okay. Here we say if the cardinality of X is n, that means if you have n elements in X, and if you have k elements in Y, then we let M to be the least integer function of n over k, the least integer function of n over k. We divide n by k, and then we take its least integer function. So you see, then there are at least m values. We have at least m values in X, which have the same image. Okay, that means m pigeons have the same, are in the same pigeonholes. Okay, here we have an example. We have in the next slide. The example is in the next slide. It's about what I am talked about before. Here we have an example. We suppose that there are 50 people in a room. Show that at least 5 of these people must have their birthday in the same month. That means we must prove that there are at least 5 people in the room which have the same which have their birthday in the same month. So how many months do we have in a year? 12. So here n is the number of people. N is the number of people in the room, which is 50. And k is the number of months, which is 12. Okay, to show that we have at least 5 people in the room which have the same month which have their birthdays in the same month. What we do, we should find m. We should find m, and m must be 5 or greater. For what? For n dividing by k. We just apply this rule. That's it. This one. Okay, we just apply that rule. It equals to, what's n? What's n? N is 50 dividing by 12. Okay, and m equals the least integer function of 4.1. Okay, so how about the least integer function of 4.1? It equals to what? It's 5. That's 5. That means m equals 5. So we prove that at least 5 people in the room have their birthdays in the same month. So we prove that. It's only the answer for that question. So easy. We say a common type of problem asks for minimum number of pigeons. If we are asked to find the minimum number of pigeons, that means we should find n in this case, such that at least m of these pigeons must be in one pigeonhole. Yeah, in this type of examples, we have m and k, but we should find n. What we do, we apply this. We say if n over m greater than or equal to k, so n over m is greater than k minus 1, and we just apply this rule. If we just memorize this rule, that's all. We say n equals, n is the number of pigeons, equal to k times m is the number of elements which have the same image, minus 1, then plus 1. We just apply this rule to find the number of pigeons or the number of elements in X. We just apply this rule. You have k times m minus 1 plus 1. Here we have an example. It says, what's the minimum number of students required in a course? That means here we should find the number of students. That means n equals to what? To be sure that at least kids will receive the same grade. That means here m equals 6, because here it says 6 of the students have the same grade. It's m. N, we should find it. We don't know the number of students. We should find it. Okay? If there are 5 possible grades, here we have 5 possible grades. So all students will take either A, B, C, D, or F. Okay? That means we have 5 types of grades. So the image, either A, B, C, D, or F. That means K here equals 5. K is the number of elements in Y. So the number of images, the number of pigeons, it's 5. We apply the above rule. We have n equals k times m minus 1 plus 1. We say we apply k times m minus 1 all plus 1. This is n. Here we have k and m. We can find n. N equals k is 5 times m is 6 minus 1 plus 1. It equals 26. Because here we have 5 times 5 is 25 plus 1 is 26. That means we must have at least 26 students in the class, such that we have 6 students which have the same grade. So it's the end of this part of this chapter. Do you have any question about pigeonholes? We have only 3 forms of pigeonhole principle. We talked about all of them and we solved the examples about each of them. If you have no questions, we start to talk about probability theory. Have you studied probability before? Haven't studied statistics? So in statistics, there's probability also. You should know probability than statistics. Okay, probability is basic things in statistics. Okay, so this section will be so easy for you. We say the theory of probability plays a crucial role in making inferences. Probability measures how likely something is to occur. Probability is the ratio of the number of favorable cases to the total number of cases. For example, if we pick a ball among, let's say, 10 balls, okay, that's 1 over 10. As the chosen one dividing by the total of ones, total of elements. Here you have these concepts: experiment, sample space, element, and event. We have these 4 concepts that you should know. Experiment is the process to yield an outcome. For example, rolling a dice. In rolling a dice, the process is experiment. The process is experiment. Sample space is the all possible outcomes. It's all possible outcomes. In rolling a dice, we have 1 up to 6. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. This is the sample space. This is all possible outcomes. Sample space is all possible outcomes. Element is an item in the sample space. In the sample space, each element, each item in this sample space is called an element. An event, an outcome or combination outcomes from an experiment. The outcome is called event. The outcome is called event. You have how to compute the probability. We assign a probability weight P of X. Here we denote probability by P, P of X. P of X, that means probability of X here. To each element of the sample space. X is the element, is an element in the sample space. Weight represents what we believe to relative likelihood of that outcome. There are 2 rules in assigning weight. We have 2 rules. We say the weight must be non-negative. That means it must not be a negative number. Okay, so it must be non-negative. It must be greater than, it must be either 0 or greater than 0. It must be either 0 or greater than 0. And also the sum of all weights must be 1. The sum of all probabilities must be 1. So each probability must not be greater than 1 and it must not be less than 0. It's possible to be between 0 to 1. And the sum of all probabilities must be 1. The sum of all probabilities must be 1. We let E to be an event. So the probability of E was P of E. As I said, we denote probability by P. P of E means probability of E equals the sum probabilities for elements in E. The sum of probabilities for elements in E. It's the sum, it's a summation. Okay. Here for probability, we say let S be a sample space. S is the set of all possible outcomes. A probability function P from the set of all elements in S to the set of real numbers satisfy the following axioms, 3 axioms. So the probability must satisfy these 3 axioms. We say the probability of A must be between 0 and A. That means it must not be less than 0 and it must not be greater than 1. Probability of each event must be between 0 and 1. It's possible to be 0 and it's possible to be 1, but not to be less than 0 and bigger than 1. And the probability of empty set, the probability of phi, which is empty set, is 0. And the probability of S, the probability of all elements in the sample space, the probability of all possibilities, as I said, S is the sample space. So the probability of S is 1. As I said before, the sum of all probabilities is 1. S is all events. So the probability of all events, the sum of them is 1. We say if A and B are disjoint, if A and B are disjoint, then probability A or B, probability A or B, probability A or probability B equals probability A plus probability B. The probability A or B means probability A plus probability B. So a function P that satisfies these above axioms is called probability distribution or probability measure. We now have complementary probabilities. We say if we have probability A to be something, how about the probability of A complement? The probability of A complement equals, as we say, the sum of all probabilities must be 1. That means probability A complement plus probability A equals 1. It must be 1. And so probability A complement equals 1 minus probability A. You have this rule. So probability of any event complement, the complement of any event is 1 minus the probability of the event. Okay. For example, in rolling a dice, if we say let X to be an event, let's say probability of 1. In rolling a dice, we either get 1, 2, 3, 4, 5, or 6. Okay, so the probability of 1 equals what? 1 over, here we have only 1. Okay, we can get 1 only once, divided by all possible outcomes. We have 6 possible outcomes. Here S is 1, 2, 3, 4, 5, 6. How many elements do you have in S? We have 6 elements. That means 1 over 6. Okay, so how about this? How about the probability of 1 complement? Let's say A to be 1. How about the probability of A complement here? It's 1 minus 1 over 6. Here we have probability of A. We say probability of A complement is 1 minus probability of A. Probability of A is 1 over 6. We say 1 minus 1 over 6 is 5 over 6. That means here, what's the probability if it's not 1? If it's not 1, it's either 2, 3, 4, 5, or 6. Okay? It is 1 over 6 is the probability of 2. The probability of 3 is 1 over 6. Probability of 4 is 1 over 6. Probability of 5, 1 over 6. Probability of 6 is 1 over 6. Summing of this is 5 over 6, as you get here. That's 1 minus probability of the sets of the event. Here, the probability of getting a prize in a lucky draw is 0.075. This is the probability of getting the prize. Thus, the probability of not getting a prize in a lucky draw is 1 minus this. It's the probability of getting the prize. Is 0.075. How about the probability of not getting the prize? Is 1 minus probability of getting the prize, because this is complement of the above one. It's 1 minus 0.075. It is 0.925. So the probability of not getting the prize is 0.925. Here we have only this rule. If you just memorize this, that's all. Now you have the uniform probability distribution. We say the probability of an event occurring is probability of E is the cardinality of E, that means the number of elements in E dividing by the cardinality of the sample space, the cardinality of all possible outcomes. Here we say E dividing by S, the number of elements in E dividing by the number of elements in S. How about the probability of, let's say, X? It is X dividing by P by S. It's anything, we divide the cardinality of this by cardinality of the sample space. Here is the set of desired events, and S is the set of all possible events. E, the cardinality of E must be greater than 0 and less than or equal to S. Less than or equal to the cardinality of S. We cannot take, let's say, if you have 10 balls, we cannot take 11 balls from 10 balls. We cannot do that. So it must be from 0 to 10. That means E, the cardinality of E, the desired events, is between 0 and cardinality of S. So that's all what you talked about. Here, an event will never happen. It's impossible event. Has probability 0. So if an event is never happened, means the probability is 0. For example, in rolling a dice, what's the probability of 7? We have no 7 on the dice. That means it's 0. Okay? An event will always happen. Has probability 1. If an event is always happen, means its probability is 1. For example, in rolling a dice, لهالداني ذلك أقبلهم جماريكم دس كبير شوتر يعني أقسام ببشش هر دس ما كيه هميشه و كاتب probability كشني ليه يك كاتب هميشه دس ما كيه. So in this case, its probability is 1. Now you have some examples. So let's take a break, then we will continue. We now have some examples. Example 1. Here it says a coin is flipped 4 times. We have a coin. In a coin, we either have tail or head. We have these two. We say a coin is flipped 4 times. The outcome for each flip is recorded. First, we should list all the possible outcomes in the sample space. So that means we should write down the sample space. So each possible outcomes. I'm going to write down all of them here. So the sample space is for part I equals. Look, let 4 of the flipped ones, I mean 4 times we get tail. That means T, 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 T. And the second one, if one of them to be hit, let's say the first one to be hit. The first time we get hit, and the 3 other times, I mean second, third, and 4th times we get tail. Here we get hit, tail, tail, tail. Then if the second time we get head, tail, head, tail, tail. Then if the third time you get head, tail, tail, head, tail. If the 4th time we get head, tail, 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 head. Then we have some more possibilities. If 2 of them to be hit, if 2 of them to be hit and the other 2 is tail, that means we have, let's say the first 2 are hit and the second 2 to be tail. Okay, and if the first one is hit, the second is tail, the third is hit, and the 4th is tail. And also you say if the first is hit, the second is tail, the third is tail, and the 4th is hit. And if the first is hit, so if the first one is tail, if the first one is tail, the second and 4th are hit, and the last one is tail. Okay, and if we have tail, head, tail, head, we also have tail, tail, head, head. And if 3 of them are head and 1 of them is tail, so you say head, 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 and tail. Then it's the 4th one is tail. The 3rd one could be tail. The 2nd one could be tail, and the 1st one could be tail also. So we have these 3 more possibilities. If 3 of them is head, that means head, head, tail, head. And also we have head, tail, head, head, tail, head, head, head. And if all of them are head, we have head, 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 head. This is the sample space. These are all possibilities in flipping a coin. أنا بارسدراي كان زي ما هي هلي شوار جار هلي همو أو حالة تانية كده اسمعنا كي بينوس همو أو possible outcome يعني كهي بينوس لا داوكراي كم داوي إما شوار جار يا هاد شوار جارك خطأ إما خطو شرمان يا هاد شوار جارك خطأ يان داني كان شيرة يان دواني شيرة يان سيانا شيرة داني خطأ ياخد هاد شواريان شيرة باش هاد شوار جارك اگر هەڵماننا هەر چوار جارێکی خەت بوو باشە ئەگەر هاتوویەک دانیان شێر بوو ئەم شێرە یەکەم جار هەڵمان ناوە شێر بووە یان دووەم جار یان سێم یان چوار کەواتە ئەگەر یەکەم جار بێت ئەگەر دووەم جار شێر بێت ئەوەی ئەگەر سێم جار شێر بێت ئەگەر چوارم جار شێر بێت ئەنجا ئەگەر دوو شێرمان ئەم دوو شێرە مەرجێ دو بە دوایە لە هەموو حاڵەتەکان ئەوێ دایان بێن یەکەم و دووەم ئەگەر شێر بن اگر یکم و سیم شیر بید اگر یکم و چوارم شیر بید اگر دوم و سیم اگر سیم و اگر دوم و چوارم واقدر سيم شوي شو حالته ما هي بين حالته ما هي شو حالته ما هي قد دوانيان شير اجا سيانيان شير يعني هسه كان بيك وين دسرتها ياخذ يكم ودوم شير سيم خطت شوارم شير يعني بو شيوه مو حالته كان من مسيوا. These are all possible outcomes. So this is answer for the first one. Now in the second part we should find the event E that coin only the outcomes in which one tails appears. If you have only one tail, so what's the event? And here we just write down the event. We don't write down the probability. We just write down all the possible outcomes if one of them is tail. Where do you take this? We take it from the sample space. We take all the events from the sample space. In the sample space, we choose all of them which have only one tail. So let's see. We have this one, and this one. That means here we have these four possibilities with one tail. So in the second part, we say E equals to what? Equals to head, tail. Yeah, we must choose only those which have only one tail, because in the question it says what's the event? Find the event which have only one tail. So we choose all of them from the sample space which have only one tail. Head, tail, head. Head, tail. Oh, sorry. Tail, head. We have only these four possible outcomes with only one tail. So this is the answer for the second part. Here, it's asking about only the events. It's not asking about the probability. So if it says what's the probability of E if we have only one tail? What's that? Here we have four possible outcomes for E. We say E, the cardinality of E dividing by the cardinality of S. That means here the probability of E equals the cardinality of E dividing by the cardinality of S. So what's the cardinality of E? E is 4. We have only 4 elements in E. And in S, how many elements do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. Divided by 16, which is 1/4. Or it's 0.25. This is the probability. But here in this example, it's not asking about finding the probability. It's only asking about finding the event, the above one. Okay? This is extra. We say the probability of E. This is the probability of E. E is the event which we have only one tail. Yeah. Which one? Sorry, it must be one. Here we have head, tail, head. It's like head, tail, head. This one is. That's it. So it is the result. This is the solution. It's only asking about this. And this one. This is the sample space. This is S. Now we have another example. It says 2 fair dice are rolled. We have 2 dice. Each dice contains from 1 to 6. Okay? Both are rolled together. Find the event E that the sum of the numbers on the dice is 7. Look, let's first write down the sample space. We should first write down the sample space, then we can find the event E. Look, the sample space equals both if both to be 1. And you have 2 dice, we roll them together. If both are 1. If the first is 1 and the second is 2. If the first is 1 and the second is 3. If the first is 1 and the second is 4. If the first is 1 and the second is 5. If the first is 1 and the second is 6. That's it. And if the first one is 2 and the second is 1. If the first is 2 and the second is 2. If the first is 2 and the second is 3. We write down them all. Okay? We pick the first one to be 1 and the second one to be from 1 to 6. And then we pick the second one to be 2, the first one to be 2, and the second one to be from 1 to 6, and so on up to 6. Okay? If this is 6 and 1, and so here we get 6 and 6 here at the end. This is the sample space. Let me show you. There is it down. Let me find it. There is that sample space here. It's written down here. It takes a lot of time. What's that? Sorry for that. I'm looking for, oh, that's it. This is the sample space. It says, find the event E such that the sum of or the sum of both to be 7. Find the event where the sum of both dice is 7. Look, this 1 plus 1 is 2. 2 plus 1 is 3. So we are going to look for those which have the sum is 7. 1 and 6 is 7. 2 and 5 is 7. 3 and 4 is 7. 4 and 3 is 7 also. 5 and 2, 6 and 1. We have these 6 possible outcomes, which the sum is 7. That means we're going to write down them. That's it. Here we have 1 6 6 1, 2 5 5 2, 3 4 4 3. We have only these 6 possible outcomes, which the sum of both occurred numbers is 7. We have no more elements in S, such that the sum of both elements is 7. Okay. So here, in rolling 2 dice together, the most important thing here is to write down the sample space. If you could write down the sample space, it's easy to answer each question about that. Suppose that a coin is flipped and a dice is rolled. Look, we have a coin was flipped, and then after a dice is rolled. We first flip the coin, and after that we dice a roll. We roll a dice. Sorry. Look, here we have and. That means first we flip the coin, then we roll the dice. It says list the numbers of the sample spaces. List the members in the sample space. When we flip the coin, it's either head or tail. It's either H or T. It's one of them. When we roll the dice, it's from 1 to 6. We have these 6 possible outcomes for the dice, and we have only these 2 outcomes for the head, for the coin, in flipping the coin. If in the flipping the coin, we get head, that means it's either head with 1. We have 6 possible outcomes for the dice, and head with 2, head with 3 up to head with 6. So if in flipping the coin we get tail, so how many possible outcomes do we have for the dice? We have 6. It's from 1 to 6. It's either tail and 1, or tail and 2, tail and 3, tail and 4, up to tail and 6. Okay, we have these all possible outcomes in flipping a coin and rolling a dice. Okay, so the sample space here is this one. It says list the member of sample space. Since you have flipping a coin and rolling a dice, in flipping the coin we have 2 possibilities, and in rolling the dice we have 6 possible outcomes. 2 times 6 is 12. So in the sample space we must have 12 elements. We must have 12 elements, as you see here. 1, 2, 3, 4, 5, 6, and here you have 6 is 12. ليرة شو مزاين sample space شو element تاعي؟ اما پارچه درای کان زایمانی هەڵماناو چەند احتیمالمان هەیە بۆ؟ 2 یان شوێریان خەتە. لە زارێکە کە هەڵیەین لە زارەکەیە چەند احتیمالمان هەیە؟ لە 1 تا 6 کاتە 6 احتیمالمان هەیە. 2 کەڕە 6 12 ئەبێ 12 احتیمالم هەبێت. لێرەش کە هەڵیەین ئەگەر هاتوو دراوکان زایەکە 2 احتیمالم هەیە یان شوێریان خەتە. ئەگەر شوێر بێت چەند احتیمالم هەیە بۆ زارەکە؟ لە 1 تا 6 کاتە یان شێر و 1 یان شێر و 2 یان شێر و 3 تا شێر و 6. ئەگە خەت بوو ئەمیش بە هەمان شێوە دیسان ئەگەر خەت بوو چەند احتیمال هەیە بۆ زارەکە؟ 6 کاتە خەت و 1 خەت و 2 خەت و 3 تا خەت و 6. ئەم بریتێ لە sample space. And now it says list the members of the event. The coin shows head and the dice shows a number less than 4. The head ones are only these. We have only these elements in S with heads. It says the coin shows heads and the dice shows a number less than 4. So 4 is not included because it says less than 4. So what are the numbers which is less than 4 with heads? We have 1, 2, and 3. That means here we have only these 3 elements. We have only these 3 elements for the second question. It says head and a number with which is less than 4. So you have only these 3 elements for event E. It says event E على event E چیه؟ ئەوەی کە شێر بێت لەگەڵ ژمارە کە ژمارەی کەمتر بێت لە 4. ئێمە شێرەکان ئەوەی سەر نووسیمانن. ئەی کەمتر لە 4 چیە؟ 1 و 2 3. کاتە شێر 1 شێر 2 شێر 3. That's all. This is the event E. Okay, try to do this by yourself now. Do it, please. It says, what's the probability? Here it's asking about probability. For the probability, we said you find the cardinality of the chosen one or the event divided by the cardinality of sample space. It says, what's the probability of picking a red marble out of a bowl with 2 red and 8 blue balls? Marbles. Okay. Here you have, let me explain for you. Here we have a bowl. In the bowl, we have 2 red marbles and 8 blue marbles. That means, what's the total of marbles? 10. So what's the probability of taking a red one? Why?
Because we have 2 outcomes of the color and the total of outcomes is 10.
Yes. Look, we have only two possibilities to take a red. We have 2 because here we have only 2 red marbles in the bowl. We have only 2 possibilities to take a red one. And the total of marbles is 10. 2 plus 8 is 10. As it says, we have 2 red and 8 blue marbles in the bowl. Here we say the number of possibilities to take a red one divided by the total of the marbles. We have 10 marbles, which is 2 over 10. How about picking a blue one? Yeah, that's 8 over 10. So it is the answer here. It says 2 fair dice are rolled. What's the probability that the sum of the numbers of dice is 10? How about this one? Why?
Because we have the 2.
How many possible outcomes in rolling 2 dice we have if the sum of them is 10? How many? Yes. Which ones?
4 to 7.
Do you have 7 in?
3, 5,
Okay. 4, 6. That's 2. No, it must be 4. How? It must be 3. Sorry. How? Yeah. We have if the first dice is 4 and the second is 6. How about if the first one is 6 and the second is 4? It's 2 possibilities. Okay. And 5, 5. We have only one 5, 5 in the sample space. It's 1, so it's 3. We have 3 possible outcomes such that the sum of both rolled dice is 10. That means یک 5 و 5 معها یکم 5 بدون 5 یکم 5 بدون فرق یک دانه بالا وانيا فرق نیه لدوباره كان یک دانه هي بلام لو يتريا جواز تشغور كيكا. So here we have 3 elements in the sample space which the sum of both elements in it is 10. 3 dividing by how many elements do you have in the sample space? In the first dice we have 6 possibilities. In the second we have 6. Multiplying them is 36. That means we have 36 elements in the sample space. So the cardinality of the sample space is 36. And here we have 3 dividing by 36, which is 1 over 2. So if the sum of them is, let's say, 7. If the sum of them is 7, how about that one? If the sum of both dice is 7, we have 6 possibilities. 1, 6, 6, 1. 2, 5, 5, 2. 3, 4, 4, 3. We have these 6 possibilities. So 6 dividing by 36. It's 1 over 6. Okay. We have another example. It says 5 microprocessors are randomly selected from a lot of 1,000. Here we have 1,000 of microprocessors. 5 of them are selected among them, which 20 are defective, sorry. 20 are defective. It says, find the probability of obtaining no defective microprocessors. Look here, we choose 5 from 1,000. And in the 1,000, we have 20 defective and 980 good ones. Okay. If we choose more than one element among a lot of elements, among the elements in the sample space, if we choose more than one element at the same time, in this case, what we do, we must use combinations. Look, it says 5 microprocessors are randomly selected. That means we choose 5 from 1,000. We choose 5 from 1,000 randomly. So ordering is not important here. If ordering is not important, means we use combination. If ordering is important, so we must use permutation. So in this case, we have combination of 1,000 and 5. We choose 5 from 1,000. And in this 1,000 microprocessors, we have 1,000. It's all 1,000. 980 is good. This is the good ones. And 20 defective. We have 980 good ones and 20 defective. We pick 5 from 1,000. Okay, we pick 5 from 1,000, and we say if these 5 are good ones, that means it must not be from the defective ones. So this 5 must be here. That means we pick 5 from 980. So the combination of 980 and 5. Now, choosing this from this, we divide this by that. اگر هاتوا ليك كاتا زيادة ليك ده أنا ما أدري هنا أو كاتا combination ده يعني permutation. اگر ordering important green boom أو permutation. برام ده ordering على random بس يعني بينشتري. وايا بينشتري إن لشيء لأنه صوها اشتاق. برام خوي مجموع كنيه 1000. هذا بينشتري مال 1000 يجي. هذا بينشتري صوها شادريني دابش كنيه بينشتري سر 1000. So you say the combination of 1,005 and the combination is 985. Okay, we say it equals to C 985 dividing by C combination of 1,005, which equals to 0.90373. If you divide 980 by 1,000, it is 0.98. It's not the same as that. Is it? It's not the same as that. You don't get the same result. So this is wrong. You don't have to do this. Because here we choose or we take 5 microprocessors together. We take 5 together. That means here we should use combinations. Do you need to find this? Or it's easy? We talked about this before. We talked about combinational permutations. So this combination is 980 factorial dividing by 5 factorial times 980 minus 5 factorial. And for the beneath one, it's the same. And for this one, we say it is 1,000 factorial dividing by 5 factorial multiplying by 1,000 minus 5 factorial. Just find this, you'll get the result. It's 0.903735781. Okay, ليرة وتماجا هاتو زيادة ليك دائما ليك هذا ده هنا أو كاتت شيكين بcombination permutation. And here we have another example about the same thing. It says there are exactly 3 red balls in a bucket of 15 balls. We have a bucket. In the bucket, we have 3 red. We have 15 balls. Let me write down 15 balls. We have 15 balls in the bucket. In these 15 balls, among these 15 balls, 3 of them is red. 3 is red. 3 of them is red. We have no more 3 ones. We have no more 3 balls. Among these 15 balls, 3 of them is red. 3 of them is red. Let me draw it better. Let's say we have 1, 2, 3, 4, 5, 6, 7. Let's say this is red, and this is red. We don't care about the other colors. Okay? We have 3 of them which are red. It says, if we choose 4 balls at random, what is the probability that we do not choose a red ball? We have 3 balls. So how many more balls do we have which are not 3? Which are not red? 12. We have 12 more balls. 3 of them is red. So the rest is 12. That means here we have 12 non-red balls and 3 red balls. It says, if you choose 4 balls at a random, here, as it says at a random means ordering is not important. And also, it says we take 4 balls together. We take 4 balls from the bucket. As we choose more than 1 ball, that means we must use combinations. We must use combinations. combination بكارهن ولا برای ordering گرینگ نیه معنی باید چیه combination. So here we choose the 4 balls from 12 among 15 balls. That means we take 4 from 15 and also we take 4 from 12. Okay, we say combination of 15 and 4 dividing by combination of 12 and that's so this is the probability of, let's say, event E. That's it. Sorry, 12 and 4 dividing by that because it's the total one. We always must divide the desired one dividing by the total one. Okay, since the total of balls is 15, so the combination of 4 out of 15 is in the denominator, and the combination of 4 out of 12 because we have 12 non-red balls. So that's all. So what if, do it by yourself, if we choose 2 balls, 2 red balls. So what's the probability of choosing 2 red balls? Do it. What's the probability of choosing 2 red balls? Choosing the probability of 2 red balls. Here, among the same. We have 3 red balls and 12 non-red balls. So what's the probability of choosing 2 red balls? So this is the result of the question. It's the answer of choosing 2 red balls. Here, the total balls is 15. That means we take 2 out of 15. And also we have 3 red balls. That means we take 2 from 3. And that's all. So it's enough for today.